This video will cover what you need to know about mass for this course. And of course, at any time, you can rewatch the video or pause it, and you can always ask me questions about it in class or by email. All right, and one advantage of doing notes by video is that you can pause it and jot stuff down. Now, you have a record because you have this video, but I do recommend you write this down. Write down what you see and you will learn it better. However, it's not required. Okay, the topic for today is the quantity mass. And you've had a homework that introduces you to what the word quantity means in science. It means something we can measure with a measuring device and describe that measurement with a number that everybody or nearly everybody agrees on. So our first official quantity in physics is mass. And here's how I introduce the topic, the quantity mass. We have a brick and we have a teacher. Which of these two things has more stuff in it? If you don't like the word stuff, matter. Which of these two things has more matter in it? Or if you know what protons, neutrons, and electrons are, imagine you add up the mass of all those, add up the matter of all of those, count up all the protons, neutrons, and electrons in me, and then in the brick, which has more. All right? I think obviously the teacher has more stuff in it than the brick. But how many times more? How could we measure that and describe that with a number? That's one of the points of today's notes, is that idea of assigning a number to this concept of having more stuff. And also, all throughout the year, I will draw your attention to this, that when we can measure something and accurately describe it with a number, and then use those numerical measurements in equations and find relations between them, that's modern science. That's one of the main differences between modern science and science that was done before, say, 1500. All right, so we picked that and we ask how many times more mass, how many times more stuff is there in the teacher than there is in the brick? How many times more matter? How numerically? So we're going to define the concept of mass. And for our quantities, we usually define them with beginning with some kind of quantifiable word, like how much or how many or how far, how long. So we define mass as this. How much? It starts with how much. How much stuff is in a thing? How much stuff is in a thing? You could also say how much stuff is in an object. That's fine. In our class this year, the word object will mean something made of matter that you could touch, feel. That's an object. But for now, I'm just going to say thing. How much stuff is in a thing? Now, this question will be on a quiz and on a test and possibly on the final. So if I say, what's Mr. Mangold's definition of mass, and you write stuff, that will only be half credit. Because stuff is matter. That's just what is in it. Mass is a quantity, which means there has to be some numerical concept in your answer. The definition of mass is not stuff. It's how much stuff. Because you could have a small amount, a large amount. How much is a numerical concept? So that's my definition of mass, how much stuff is in a thing. You will see other definitions. A textbook, a professor may give you a different definition having to do with inertia, how much something resists a change in motion. That's fine, there's nothing wrong with that. But at this beginner level, I think this is a more basic concept and it connects more clearly to the ideas of gravity and Newton's laws. How much stuff is in a thing? If the word stuff bothers you, you can write how much matter is in a thing. All right, we will have equations that will have symbols in them, and those symbols will stand for quantities. For example, there's mass, there's force, there's acceleration, and I don't want to write out those whole words in these equations. So every single quantity we learn will have a symbol to stand for. Here I'll use the word abbreviation. Later on I'll start using the word symbol. So we will have, for example, Newton's second law is force equals mass times acceleration. Nobody wants to write out those entire words. So we have a single letter to stand for the word mass. Take a guess, a wild guess what it is. Of course, it's an M. And you're allowed to use lowercase m, or you can use a capital M. And we tend to use lowercase m's when we have one object and capital M when we have multiple objects, and maybe the capital M is the total mass, but it doesn't matter. M is the symbol we use to stand for the word mass whenever it comes up in an equation. Okay, I'm going to clear the board here and put up some more notes. Now, you look at that M I just wrote, you may think, wait, doesn't that stand for meter? That's a different thing. That's the unit that you would use to describe a quantity. And all year long, I'll stress the difference between the symbol that stands for a quantity and the symbol that stands for a unit. Those are two different things. And look what our next note is. Our next note is on the concept of a unit for mass. And I better explain what unit means. Unit means unit of measurement. It means some standard we all agree on to mean one of something. So for example, if you're driving in the United States on a road, what's the standard unit of measurement? So if someone says, how far is it to the next town? I say, oh, about 40, maybe 45. They don't mean inches, right? They mean miles. So the standard unit of measurement we agree on, that if someone says, oh, it's just one, we just have to drive one more, that means one more mile on a road. Well, we have a standard unit of measurement for mass that scientists all over the world agree on, and it's the gram. The gram, that's how you spell the word. And once again, we don't want to write the word every time we use it, so we have an abbreviation or a symbol for the word, and it's a lowercase g. Never a capital. In this class, always a lowercase g stands for gram. And a gram is about the mass that one large paperclip has. Next, note F is typical values. And everything in these notes will be in the quiz on mass. So when you study for that quiz, you want to study the notes you took on this. You could also study the video, but videos take a long time to look at. You could take screenshots and study the screenshots, whatever works for you. These typical values will be on your next quiz. Anytime you learn a new quantity, especially if it's one you're not used to using, and it has a unit that you don't use every day. You don't use grams and kilograms every day in your life. So every time you run into a new unit, it's a good idea to get some typical values in your head. Then you will catch mistakes. For example, if you did a calculation for how far a car was driving, and you calculated that the car was driving on Highway 50 at a speed of 15,000 miles per hour, you would know that you made a mistake because you know the typical value for a car on a highway is about 65 miles per hour. So if you know typical values, you can catch your own mistakes. So here's some typical values that I want you to have memorized for your test, quiz, and final. The first is the typical value of the mass of a paperclip. So there's a paperclip. Okay, one large paperclip typically has a mass of about 1 gram, 1 g. Our brick, that's what we're going to call this thing. This brick that I held up at the beginning of class and compared to myself. We're going to call that our brick. You get those from a science supply company. They have a hook so you can hang them on things. And they're machined to have a mass of 1,000 grams. 1,000 grams, very accurately. Like it'll be off. It might be wrong, but it'll be wrong by less than a gram. So this should be 1,000 grams. And I have about 20 of them because they come in handy for certain labs that we do. So we call that our brick, and its mass is 1,000 grams. Now, because a lot of masses like people and cars and planes are so large, for the objects in physics, most of the time we do not use g and grams. Most of the time we use kilogram. And look at our brick here. It has a mass of 1,000 grams. The word kilo just means 1,000. It's a word that means a number, just like dozen means 12. So like, for example, 1 dozen grams would be 12 grams. 1 kilogram means 1,000 grams. Kilo means 1,000. And of course, once again, we don't want to have to write this all out. It takes too long. So kilo has a symbol, an abbreviation, and that's a lowercase k. Never a capital, always a lowercase. So if I ask you, what's the abbreviation for kilogram? You have to write a lowercase k and a lowercase g. If you make either one of them uppercase, you lose credit. Right? So now look at what we've covered in this. When you look at this now, you should be able to say the word 1 kilogram, and you should know what all of it means, 1,000 grams, and you should know that the gram is the most basic unit for mass, and it's the mass of 1 paperclip. And 1 kilogram means 1,000 grams, which is the mass of our brick. Okay, so look at me. right? 6'1", you can see, on the skinny side. Okay? And try to estimate my mass in your head. You know that our brick is 1,000 grams, or 1 kilogram. Try to estimate my mass in kilograms. All right, roughly I'm between 70 and 80, depending on what kind of running shape I'm in and if I'm training for a race. But I've been using this for the past few years because I've been running in marathons. So we'll put 70 kilograms. So that's a mass of a typical adult my size, 70 kilograms. So right away you might start thinking about whether you are less than 70 or more than 70 kilograms. Now let's take a teacher, if you know Ms. Jacobson, for example. Would she be less than 70 kilograms or more than 70 kilograms? She would definitely be less than 70 kilograms. All right. And then finally, for something bigger, I'd like you to have an estimate of the mass of a small car. This is a small car, a compact car, not a typical large sedan type car, like not a Dodge Challenger, not my wife's Tesla Model 3, but a small car. And the mass of a small car, not that small, right? But the mass of a small compact car would be conveniently about 1,000 kilograms. Notice, since this is big, right, this is a big object compared to a paper clip, I'm going to use kilograms as my unit, not grams. Because if I use grams, I have to write 1,000,000 grams. That's a lot more to write. But this is why we use kilograms typically when we describe the mass of, say, a car or a person or a brick. It's a lot quicker. 1 kilogram, 70 kilograms, 1,000 kilograms. So those are the typical values I'd like you to know for the next quiz, for the final. For car, there's a lot of flexibility. If I ask you what might be the mass of a small car and you put 800 kilograms, fine, 1,100, fine. If I just write car, you could put 1,500. That'd be a perfectly fine car. In fact, our Tesla Model 3 is about 1,800 kilograms or so. There's a common confusion between these two words, mass and weight. In everyday life, they're used as if they mean the same thing. But you need to know how they're used in science. They do not mean the same thing in science. So we'll start this discussion today, but we'll build on it later. First, we'll look at what they are. We just learned what mass is. On the quiz, if I ask, what's Mr. Mangold's definition of mass? And by the way, if I say, what's Mr. Mangold's definition of mass? You cannot write a definition you looked up somewhere. You have to write my definition. My definition is how much stuff. How much stuff is in a thing? Right? In science, and if you already know this, you should guess what the answer is going to be. In science, the word weight specifically refers to a particular force, a pulling force. And if you know what that is, take a guess. Okay? Weight refers to the pull of a planet's, pull of the local gravity force. We will learn about the gravity force. We will have notes, lessons, lab, homework. So we will learn a lot more about the gravity force. So if this does not make complete sense to you now, that's okay. We will learn more. So it's a pull of the local gravity force on a thing. It comes from outside. It's a pull from, say, on us right now, on the Earth, pulling down on us with the gravity force. And I'm going to draw an arrow to stress that that's a force that pulls down on something. So look, this one, mass, is internal. It's how much stuff is inside an object. This is external. This is the gravity force that pulls down on a thing. All right? The unit, what we just learned, the unit for mass is the gram, or for convenience, you can use the kilogram. This is not stuff. This is not mass. Weight is not mass or stuff. It's how strong a force is pulling. So it's a force. And again, if you think you know a unit for force, you should think that in your head, pause the video, and say it to yourself, maybe write it down and take a guess. Well, in metric, the unit for force is the Newton. And in English or American units, it's the pound. So see, it's a completely different unit. Grams, kilograms tells how much stuff is in something. That's the unit for mass. Newton or pound tells how hard you push or pull on something. You could be lifting weights, and the weights would have a certain number of pounds printed on them. That's how much force you have to apply to hold that weight stationary in midair. All right, so it's very different things. And now think about how this leads into the last line here. If I have, say, a person like me, do you remember what my mass is? It's 70 kilograms. That means that's how much stuff is in me. Do you remember the mass of this brick? It's 1 kilogram. That means that's how much stuff is in this, 1,000 grams. This is like 1,000 paper clips. And I'm like 70 of these. So I'm like 70,000 paper clips. That's how much stuff is in something. But the weight force is the local pool of gravity, and I think just about everyone, I've done your first handout, just about everyone seemed to know that the force of gravity was different on the moon. So we asked this question, is this a thing that's different on different planets? If my mass is 70 kilograms on Earth, if I go to the moon, is it still 70 kilograms? Don't try to answer that using what you've learned before this class or the way people speak in everyday life. Use only what was in today's notes. If I go to the moon, is my mass less than 70 kilograms, equal to 70 kilograms, or more than 70 kilograms? So to answer that question, you have to go back to what mass really means. How much stuff is in something? If you take me and put me on the moon, or you take this brick and put it on the moon, does the amount of stuff in it magically change? And of course the answer is no. So mass, is it different on different planets? The answer is no. Because mass means how much stuff in science. Same amount of stuff in that brick, still 1 kilogram of stuff on the moon. But look at this. Weight is a force. It's a pull of gravity, and you probably know that the gravity force pulls on you on the moon more weakly than it does on Earth. It's stronger on Earth. You may know that if we could put you on Jupiter, it would be stronger on Jupiter than it is on Earth. If we could put you on the sun without you being burned immediately, it would be much, much stronger on the sun. So the pull of gravity on you or this brick is different in different places. It's even different in different places on Earth. If you're really low, like in Death Valley, the pull of gravity will be stronger. If you're up high, like on Mount Everest, far away from the center of the Earth, the pull of gravity will be weaker. So is this different on different, is weight force different on different planets? The answer is yes. So this is the scientific way that these two words are used. They do not mean the same thing in science. Mass means how much stuff. Weight means how strong the local gravity force is on the object. And from those two meanings, from those two definitions, everything else follows. You may be asking in your mind, well, why do people seem to use these to mean the same thing in everyday life? How come in other countries, for your weight, it has your mass in kilograms? Why are they so confused on Earth? And the reason is that one's proportional to the other. In fact, we'll learn that if you're in metric, your weight in newtons is 10 times your mass in kilograms. If we just take your mass in kilograms, for me that'd be 70, multiply it by 10, we get the gravity force on me as 700 newtons, but that's only true on Earth. The reason that these are interchangeable almost on Earth is that they're interchangeable in everyday life is we're all on Earth all the time. So they're proportional to each other. But if we went into outer space, this would suddenly shrink to zero, but your mass would stay the same. And we'll finish up with this idea. How do you measure mass? This will draw attention to what mass really is, emphasize how much stuff is in something. It will also point out how mass and weight are different. All right, there's several different ways to measure the mass of an object, and I apologize, but the camera's going to be moving around a little bit as I put different objects in front of it. All right, the first way you may have seen to measure the mass of something is to use an electronic balance, and this is what an electronic balance looks like. It's plugged in. They're highly accurate, sort of, and I'll explain what that means in a second. They're very accurate, and we'll zero this out. And I think I have a paper clip somewhere. Yeah. So right now it's set to 0. Here's a paper clip. All right, put that on here. And it reads 1.02. So it's reading 1.02, which is what we'd expect. We'd expect this to be about 1 gram. You see a little G there for grams, 1 gram. So that's an electronic balance. Electronic scale, electronic balance. Okay, but think a minute about how this works. This works because you put something on it. Whoops. You put something on it, and that thing, that paper clip, pushes down on the little metal tray, and this measures the push. And what it does, it's actually measuring the push as a force, and then it's figuring out what the mass would have to be to create that push. Why does this clip push down on the tray at all? Well, it pushes down on the tray because the clip itself is being pulled down by a force. What force is pulling down on the paper clip? The force of gravity. So gravity pulls down on the paper clip. The clip pushes on the tray with a force, and this does a calculation to figure out how much mass there must be in the paperclip for that to happen. In other words, this has built into it a divide by 10 thing. This knows it's on Earth. So it takes the force that the paperclip is pushing down on the tray, divides that by 10, and it figures that must be the mass of the paperclip. So do you hear what I said? This is set up to work only on one planet. This is set up to assume, it assumes that it's on Earth, and it does the calculation to figure out the mass of this paperclip based on the gravity force pulling down on the paperclip on Earth. All right, so our little electronic scale there seems like it would be the best way to measure mass. It's electronic, it seems very accurate, but there's a problem with it. The problem with this electronic scale, if you look at it just like universally, is it's correct only on Earth. It uses Earth's gravity. And since this is the beginning of the year, I want to keep stressing gravity as a force. It can also be called the weight force. Oh, I'm getting a text, so let me turn that off. Sorry about that. Turn the phone off so that doesn't happen again. So this works only on Earth. That's correct, only on Earth, because it uses the Earth's gravity. You may think, well, what's the big deal? We're always on Earth. Not everyone's always on Earth. They go up into space, into the space station, which orbits the Earth, or ships that have gone to the moon and back. And when something's in orbit, the force of gravity is canceled out and has no effect. So this scale will not work in the space station. And they perform experiments in the space station. They have to measure out a certain amount of mass for things. This scale will not work in outer space on the space station. So it's correct only on Earth. It works only on this planet. All right, so let's look in a more old-fashioned way to measure mass. That's this. This is a balance, and you can see 3 different scales on it. This is what you call a triple beam balance. You can put an unknown in it, move these around. Well, that's pretty good. Okay. The way this works is like a seesaw, a teeter-totter, a seesaw. There's a pivot point right here. You put your unknown here, and then you move these bricks back and forth, and you read, and you can see in this case, the mass of this is about 100 grams. It's supposed to be 100 grams, and that's really close. And it balances. That's why it's called a balance. Triple beam because there are 3 scales, 3 sliding bricks. So I would ask this question. Clearly it works on Earth. Would it also work on the moon? The electronic scale we had before is correct only on Earth. If you put it on the moon, it will give you the wrong reading for mass. But what about this? Will this be correct on the moon? So think for a minute. If you were on the moon, the gravity force would be weaker. So the pull on these bricks would be weaker. But what? But the pull on the unknown would be equally weak. So you'd have a weaker pull on both sides, so it's still balanced. If I took this thing, could pick it up and magically just suddenly go to the moon and set it down, it would still be in balance because the force on both sides will be 6 times weaker, 1/6 the strength. So this balance beam would still stay in balance. So this would actually, in some ways, this is better than the electronic balance, Because this will work on any planet, because all it requires is that seesaw effect. It doesn't do any complicated division like the electronic one does. All right, so this, the beam balance, will be correct on any planet. So in a way, it's better. But once again, think about the space station. What if we take it out into space where there's no gravity force acting on it? This needs gravity to pull down on both sides. If there's no pulling down, if this can just float off as soon as there's a little bit of air, if someone talks and the air blows on it, and it'll just start floating away because there's no gravity, this will not work. So this one here, this electronic beam balance, it's correct on any planet, but it needs gravity force. It needs there to be some gravity force. It doesn't have to be Earth's gravity for it to be correct, but it does need some gravity force. So it's no good in empty space. All right, so once again, this will not work in the space station because this requires a gravity force to pull the objects downward. This does not work on the space station. So what will work on the space station? Well, you probably have a good idea from the lab that you did. This is the shake tester. You saw this in the lab. It goes back and forth like that. You can put an unknown in it, put an object in it, it goes back and forth more slowly. Right? If I put even more mass in it, it goes back and forth even more slowly. Right? So the rate of going back and forth for this changes depending on how much mass is in it. If there's no mass at all, we'll get it going and hold it. It goes wobbles very quickly. If there's some mass, it wobbles more slowly. So this can be used to measure mass. But will it work in empty space? Will it work on other planets? And the answer is yes. And here's why. It has two metal arms. The reason this moves the way it does is not because the gravity force is pulling down on it. It's because these metal arms get stretched to one side and they pull back. It's very similar to your own arms. You have muscles in your arms. And let's say I take the unknown. On Earth, I can do this. I can pull it in towards myself. Was that because the gravity force is pulling downward on this brick? No, absolutely not. It's because I have muscles in my arm and I contract those muscles and I pull the brick towards myself. Likewise, the shake tester has these metal arms, and when they're distorted or stretched, they pull back. And the farther they get distorted, the stronger they pull back. And that's why they pull this tray to the middle. At the middle, their force has now gone to zero, and that's why it slides through the middle to the other side, where the arms try to pull it back again. But as they pull in, unlike your arm, as these arms pull back and become normal, their force goes to zero. They become out completely weak here, and that lets the tray slide through, and that's why the tray wobbles back and forth. So this thing here does not need gravity. So let me slide this camera so you can see better. Okay, the shake tester, or inertial balance, also called. It uses the arms, not gravity. It uses the arms, not the gravity force. So it works everywhere. And I'll just say something. You won't be tested on this, but I just want to say something. These first two measuring devices are using the property of matter and mass that they are affected by gravity. That gravity pulls on matter, and the bigger the mass, the bigger that pull. So that's what these two use. But the shake tester does not use that property. Mass has a second property, which is that it inhibits motion. It resists changes in its motion. So when I take the shake tester, and I put mass in it, it resists the changes that the shake tester wanted to do before. And so the back and forth changing of the motion occurs more slowly because there's mass. So because this shake tester uses a different property of the mass, it doesn't depend on gravity, it works everywhere. This is how they measure mass in the space station, for example. They don't have that flimsy thing with the metal arms. They have sophisticated electronic devices that shake something side to side, and they measure how hard it is to shake, and that way they figure out its mass. Right, and the last test for mass is also works everywhere, is independent of gravity. And this is my own little kind of joke about mass, but it helps lead into the idea of momentum that we learn in a couple of months. And that's called the damage test. And the idea of the damage test is, imagine you take this brick. All right, now this is a bit gruesome, but imagine you take this brick and you throw it at somebody. Let's not throw it all that hard, just hard enough so it kind of makes a bruise. And if you don't like the brick idea, imagine throwing something, I don't know, like a baseball lightly, it makes a bruise. Okay? It makes that bruise for two reasons. One is how fast it's going, right? And the other is how much mass there is. Obviously, if we throw a paper clip, okay, and a brick at you at the same speed, which one are you going to duck? And which one is going to hurt you more? If they're coming at you at the same speed, paper clip or brick? And of course the brick is. Why? They're both made out of metal, right? They're both roughly equally hard. They have equal hardness. So why would the brick hurt you more than the paperclip if the speed's the same? What's the difference between these two? And of course, it's because the brick has 1,000 times more mass. 1,000 grams, or a kilogram, and 1 gram. So that's another effect that mass can have that's connected with the idea of momentum. More mass equals more damage. Officially, we'd say more mass at the same speed creates more momentum. But that's yet another way to measure mass, is by how much damage the mass does when it hits something. And of course, other things matter, like how hard the moving object is. But let's say all those other things are equal. Same speed, same material, same hardness. Of course, something with more mass is going to cause more damage. That also has nothing to do with the downward pull of gravity. The only thing that is affecting it is how fast that brick is moving. That's it. So this is yet another way we could measure mass without anywhere, even where there's no gravity involved. But of course, no one actually measures mass this way. That's silly. They measure mass this way when they're in a zero gravity environment.